This is Saxon Advanced Math Law of Cosines, and we're going to jump right into here. We've already understand the law of sines, sine A over A, sine B over B equals sine C over C, or you can do the reciprocals of those. And we've already used those to find unknown parts to triangles that are not right triangles. We're going to add another formula, if you will, into this. So our first formula that we learned with unknown parts of a triangle was the Pythagorean theorem, and you learned that years ago. So this is just adding to our repertoire. This is adding to what we know we can use. So we went from it has to be a right triangle, and you have to know one or two of these other pieces of the right triangle to solve for it, and then that was Pythagorean, and then we went to the law of sines that said it didn't have to be a right triangle, but you had to have a pair. But sometimes you don't have pairs, and we're going to get into that. And when you don't have a pair, you're going to use the law of cosines. Now, let's look at our triangle, and we'll just as a quick refresher here, and I threw a triangle here in the middle to see. The first thing I want us to remember as a point of review is the common labeling of uppercase and lowercase. If you remember the Pythagorean theorem, a squared plus b squared equals c squared, and you always see it lowercase or written in lowercase, and the reason for that is those are side lengths. Unknown side lengths are lowercase. Unknown angles, however, are uppercase. And I went ahead and wrote those on here in that format. And you can notice that A goes with A, and B goes with B, and C goes with C. A little hard to tell the difference between a capital and lowercase c, but you get the general idea. Those pairs are working together, and we're going to use those pairs in such a way to solve for an unknown side. Now, when you, or an unknown angle. When you had this originally with the Pythagorean theorem, you were told, hey, C always has to go with the hypotenuse. So a squared plus b squared equals c squared, and C has to be the longest side. And you learned it that way because that was the only way that the Pythagorean theorem works, and you had to subtract if you wanted to get, if you were finding for it, for instance, A, you would realize that a squared equals c squared minus b squared when you're finding for another unknown side. But it didn't matter which was A and B. Those didn't make a difference. Well, with the law of cosines, it's even easier, and the law of sines, it doesn't matter which one is A, B, or C, as long as you're working with them with pairs. Now, the book takes the time to write it out as c squared equals A squared equals B squared equals. I only wrote it in one way for the law of sines, or law of cosines, because it doesn't make a difference because I'm going to relabel my triangle to make it fit the law of cosines. So rather than memorizing all three that are just the same thing, I'm going to memorize one and then make the triangle fit the formula I've already memorized. So if you notice, c squared equals a squared plus b squared minus 2ab cosine c. This is the pair that I have to make this work. The nice thing is in unknown parts of a triangle, if you have enough parts to solve for it, you either have law of sines set up or law of cosines set up. And we're going to look at that in just a moment on which one to use where. So this right here, if you use this on a right triangle, and you said, well, then in a right triangle, C has to be the longest side, and that's fine. Then this is going to be 90. Cosine of 90, quickly, we know that. That's 0. So you ending up with the Pythagorean theorem. There it is hidden in there. So we already know how to work with this a little bit, but let's jump right in on 81.1, and we're going to look at this example. They're saying solve for these unknown parts. Now, the issue is, as we go through it, we go through our steps and we say, is it a right triangle? Well, no, so I can't use the Pythagorean theorem. If there's a pair known together, okay, so 36 and x would be a pair, y and 10 is a pair, 7 and m is a pair, no pairs. This is where the law of cosines comes in and really shines through as our only option, or at this level our only option. And so what I'm going to do is I'm going to say, well, I'm going to relabel this, and I'm going to say that my c and c are 36 and x. And that's very important that I relabel it that way. A and b don't make any difference, but they do have to go together in their pairs. But because they're being squared and added and multiplied together here and added, or multiplied together, it doesn't matter which one is A and which one is B. The only one that makes a difference is our pair. So we're looking for pairs. Because I only have one angle here given, I'm going to have to use the pair of x and 36. So I'm going to look at this and realize that my unknown side, x squared, equals 10 squared plus 7 squared. It wouldn't matter if I did 7 squared plus 10 squared. It's the same thing. So I'm just ignoring whatever a and b is. It makes no difference. I'm just going to put them in. 10 squared plus 7 squared minus 2 times 7 times 10. And I did this on purpose. A I used on this one and A used this one. Because if they're being multiplied, it makes no difference. Cosine of 36. And I go ahead and start working this out. 10 squared is 100, 7 squared is 49, 100 plus 49 is 149. I'm going to do 140 times the cosine of 36, get 113.26. I subtract that from 149. Keep in mind I have to be in degrees. When I do so, I'll get 35.74, and that's what x squared is. But I don't want x. I want x squared. I take the root of both sides, and I get 5.98. Now, we have drilled into your head throughout this year, there's more than one answer to these things, right? But in this case, there isn't, because x would have to be a negative 5.98. If that was the negative side of that, I don't know about you, but that triangle having a length that is a negative could be a problem, because I don't know how you have negative lengths of sides. So we only are going to use the positive root. At this point, I now have a pair. I could go back and solve using law of cosines. We'll look at that in a minute here on why I would or wouldn't do so. But at this point, I'm going to just go ahead and jump into the law of sines, because the law of sines is so much quicker, right? It's just 2 steps instead of multiple steps of solving. So I'm going to set up my pair that I know, 36 and 5.98, and say the law of sines says, and it doesn't matter, once again, A or B or C, as long as I'm keeping them in pairs. Sure, the formula says A over sine A, B over sine B, C over sine C, or you can use the inverse, sine A over A, sine B over B, equals sine C over C. That's okay, but you have to realize that it doesn't matter which one's A, B, and C. So all I'm going to do is look for pairs. If I wanted to use these pairs, I'm going to say 5.98 over sine of 36. And I'm going to be looking for the y, so I'm going to say 10 over the sine of y. There's my next pair. When I solve this out, I get 2 possible answers. I get 79.39 or 100.61. This is where my diagram is key. The 79.39 is an angle of y, so is this less than 90 or greater than 90? Well, I'm going to have to look at that and realize this is greater than 90, and I'm going to use the 100.61. Now, where did the 100.61 come from? When I did this, I said 79.39, okay? And I realized that that could be in the first or the second quadrant. 180 minus my 79.39 gives me my 100.61, and that's the angle that I'm going to use in here. Okay? Now, they use the law of sines again to find this last angle, although those of you who are astute would realize I could just very easily say 180 minus 100.61 minus 36 has got to be m. But if I go ahead and use the law of sines again, 5.98 over sine 36 equals 7 over sine m. When I do so, I end up with 43.47 or 136. Notice these are supplementary. They add to 180. So it could be in the first or second quadrant. It could be an acute or obtuse triangle. And I'm looking at m and I'm saying that's obviously acute. So I'm going to use the smaller one. That's why I circled it. So those 2 are there. Now, if I choose to use the law of cosines for this, and I won't go through all the steps, but if I chose to use the law of cosines solving for y, I could do so. And it is going to give me an answer that is exact without having to think about it. Okay, and the reason why is because the law of cosines, when solving for that angle up there, is going to automatically give me the correct version of that because the sides are known. If both sides are, or all 3 sides are known like this, it's going to give me the only angle that works. Now, there is an ambiguous way of looking at this, and we'll go back to that in just a minute after 81.4, because I did go ahead and work it out and show you why there's an ambiguous version. But not of this one. This will always give it to you, right? And you can always use the law of cosine. It just takes a little longer. But if you have your diagram, you don't need to go all through all that. Okay, look at 81.4, and it says find this unknown side. And I'm skipping a couple of them because they are very redundant in this lesson. 150, 50, and length L with a 15-degree separation. Okay, now they labeled this as lowercase l. I went ahead and put the label of uppercase L in there because they're a pair, right? And that's how I'm going to know them. And I go ahead and use the law of sines, and I say 150 over the sine of b, and that's because these are my pair, equals 50 over the sine of 15. There's my other pair. When I do this and work this out, and for time I will skip it, you will get to the sine of b is 0.7765. And you say, well, okay, well, what is that? Well, that would either be second sine of 0.7765 is 50.94. But so is the supplementary angle of that, which is 129. And I'm going to have to look at b and say, is that acute or obtuse? And that's obviously obtuse, and so I'm going to use the larger one. I can subtract to find the last one at 35.94. Okay? To find length L, I go ahead and do the same thing, and it will, when finding for the law of sines for an unknown side, it's always going to give me a one answer, not two, and it works out as 113.39. That brings me to a little bit of the bonus on this lesson. What if I were to do the same problem, but not use the law of sines? Could I come up with it? And yes, I could. I went ahead and used the law of cosines. And so 50 squared, right? There's my c, and my 15, there's my other c, right? So I use this pair, because I have a pair, and I use the 150 squared, that went in here, plus L squared, it's unknown, minus 300, right, because that's where that's coming from, I'm sorry, minus 2 times 150, which is going to be 300, times L, times the cosine of 15. Now, here's where this becomes interesting. I've used L twice, and one of them is squared. I end up with this quadratic version right here, L squared minus 289.77L plus 20,000, and that equals 0. Well, that's great, but this looks exciting, right? So I stuck this into our quadratic equation, our formula, and this quadratic equation in the quadratic formula, and I end up with this long version here, which I'm not going to belabor. You guys already understand how to use a quadratic when you are solving for a variable. When I get to the end, I get two possible outcomes, right? 176.37 and 113.38. Now we can already see that this L here is going to be correct, but why? And the reason why is, and I'm going to sketch a little bit on this triangle here. If you were to think with me, all we knew was this was a 150 and this is 50, and that's 15. Is there another triangle that exists that would give me that other answer? And there is. I have to admit, it did take me a second to figure this out. If I were to look at this, and that's just because it was turned sideways, I guess, I don't know. I just looked at it, I couldn't figure that out for a minute. But then I realized that this triangle 50, this length here could be 50, and that length could be 50, and it'd be in the same triangle. So is this an acute with another acute angle up here, or is it acute with an obtuse angle up there? Because it either way works out. And that would give me either an overall length of 176.37, which would be if it was this length, or 113.38, which was this length. So sometimes solving with the law of cosines would make me have to look at this and realize, well, is it the shorter version or the longer version? Well, on this one, it was the shorter version. I can see it. But I have that possibility of getting an ambiguous answer, or a possibility of two answers because of the root, right? Because of the plus or minus. So I have to be careful with using law of sines, law of cosines, because depending on which version I'm doing, when I'm solving like this for this side L, this law of sines always gives me only one real answer. But if I'm solving for an unknown angle, right, like I did over here, there were two possibles in the law of sines, but the law of cosines nailed it down to one right away. So sometimes one way is better, sometimes the other way is better, but the law, this is just kind of an interesting way to look at it. The law of sines, law of cosines can be used either way interchangeably on these that you have, because you can always come up with your pairs. However, sometimes you have to start with one and realize there is no other way in this case here. Too many variables, right? And so each one of these have their pros and cons. Just make sure you're watching your sketch to look, is my answer logical? If I come up with 170 and I've got a little tiny angle, it can't be, right? Is it greater than 90 or less than 90? And you should be able to look at your diagram and know the answer to that.